All good? Okay. Shall we start? Let me... Yeah, if you can fix the camera concurrently, that'd be good. I don't know why these things are not very robust. Okay, the sound is better too. It was too loud, I think, earlier. Okay, let's get started. So today we're going to cover memory controllers, but as you know, we've been covering memory controllers for a while, but now we're going to do a little bit more in-depth treatment of what they do and why they're so important and why they're getting even more important into the future. Like from my perspective, we spend a lot of time optimizing the processor, but everything goes through the memory controller. Everything, meaning everything in the system goes through the memory controller to access main memory. And I don't believe we do enough diligence to optimize the memory controller as much. Partially because one of the main reasons, in my opinion, is really we are very processor-centric. Processor. Everybody has processor in their heads. And everybody's educated with processor being almost the only thing that is executing programs, etc. And as a result, other parts of the system are kind of ignored by most people. This is really inherent in the thinking, educational system, and also the way industry operates in general, right? Industry values processors a lot more. Why? Well, I think there are business reasons, etc., that are not really nice, in my opinion, overall. But I think we should be doing a lot more diligence to memory controllers. So I think hopefully this gives you a little bit of the mindset as well. So, okay, so what's a memory controller? Essentially, long latency memories have similar characteristics that need to be controlled. I will use DRAM as an example in this lecture, but scheduling and control issues are similar in the design of controllers for other types of memories also, like flash memory, as we will see later on. Emerging memory technology, as we will see a little bit earlier than flash memory probably. We're going to talk about some of these. But these other technologies actually potentially place other demands on the controller as well. Some of these technologies have, actually almost all of these technologies have endurance issues. Whenever you write to a cell, you destroy it a little bit. So you cannot do more than some number of writes to the cell. And the controller needs to deal with it. This is a first order job of the controller. How do you ensure that a cell doesn't wear out so that you don't lose data? Right? This is not a problem in DRAM currently. So there are other things that other memories impose. So you always need to design the memory controller to control a particular technology. Some of the things that you do are more or less independent of the technology, like scheduling requests, etc. But there's technology-dependent aspects of it also, because if the technology, for example, is in such a way that accessing one cell is faster than accessing some other cell, now that controller can take advantage of it. So there could, the design of the controller has technology-specific aspects, but also some technology-agnostic aspects as well. So it's good to understand what those are so that you can actually create effective controllers. Okay, and we've always argued in this course that you should be designing the controller so that you can make the technology, underlying technology, even more effective, right? We've seen that with RowHammer, for example. We've seen that with data retention, etc. Today, we're going to look at issues like scheduling, etc. Before I go into DRAM a little bit, let me give you an example from SSD controllers. We're going to see this more. But SSD controllers essentially control flash memories. Today, SSDs are made of flash memories, usually NAND flash. There's also NOR flash, but it's a very small portion of the SSDs that are manufactured today because it's not as scalable as NAND flash today. But essentially, SSD controllers are flash memory specific. They need to deal with the characteristics of the flash memory chips. For example, there's sophisticated error correcting codes, as we will see later on. There are sophisticated mechanisms for wear leveling, meaning leveling the wear out across different cells so that no one cell goes bad much earlier than other cells. They do a lot of voltage optimization so that the data that you read is actually accurately read. You don't get errors, or you minimize the errors so that error correcting codes can correct them. They do things like garbage collection, because whenever you write to a flash cell, whenever you erase a flash cell, you need to reallocate it potentially. There's an erase operation that we will see when we talk about flash that doesn't exist in DRAM really. So that's page becomes invalid and that block becomes invalid, then you need to actually collect it and reuse it later on. And then there's also page remapping mechanisms that happen due to multiple reasons, partially because of garbage collection, unallocated blocks, but also very leveling. So an SSD control is actually quite complicated, and we will see this more when we discuss flash memory. But keep this in mind. So there are a lot of tasks over here, as you can see. For that reason, this SSD controller usually has like hardware components that are specialized to do particular things like ECC, for example. There's hardware level ECC over here, also scheduling, etc. But also it has software components to do some other things like wear out management, garbage collection, etc. So there's a full processor that exists in SSD controllers today. In some SSDs, actually, you have 8 different cores over there trying to manage this memory. So if you look at this is kind of like a system by itself, right? Although there's a connection to the host, which could be the CPU. Internally, you actually have a lot of things. There's buffer manager, but that buffer is DRAM. So there's internally a DRAM controller inside the SSD too. So it's fascinating, I think. So this picture should make you think a little bit, right? We're designing a system just to get data out of storage. And this system is there. It's actually quite general purpose. And we're treating as only a servant to the CPU or GPU or whatever you connect this to. Does it really make sense, right? You're really designing all this complexity in the system so that you can get the data out and send it to the CPU and back and forth and back and forth. It's good to think about what else can you do with this system over here, right? That's why I think memory controllers are actually extremely important. But people need to think about them differently to really make them much better. Okay, so this is a better picture, perhaps, from one of our papers where we summarize a lot of the works on how SSD controllers operate to manage errors. If you're interested, you can take a look right now, but we're going to look at it more. So there are other things that this controller does actually, like scrambling of the data so that you get better power distribution, etc. Encryption, potentially, compression, potentially. So there are a lot of tasks over here that the processors or hardware units over here do to manage data. Okay, and this is the paper where this picture comes from, and I'd recommend it to you multiple times. I actually showed this, but I believe it's a very good introduction to SSDs. So error management is a big task of these controllers, as we have seen in DRAM. In DRAM, we talked about robustness issues, retention issues, etc. Refresh, those are essentially error management issues, right? Refresh is, in my opinion, an error management issue, integrity management issue, because if you don't do that, you get errors. The reason we're doing refresh today is to prevent errors and data corruption, to maintain data integrity. True for RowHammer as well. So if you thought those errors were like ominous and a lot, once you look at other technologies, you'll see a lot more errors. So this is just our characterization from that paper that I mentioned. But you get wear out errors, for example. You get errors when you program cells. You get errors similar to like when you actually do something to a cell, some other cells get interfered with. You get data retention errors like in DRAM, and you get read disturbance mechanisms that are slightly different from DRAM. And for these, there are different mechanisms for these errors, and there are different techniques that are developed also to handle these errors. So this paper categorizes the error types as well as the mitigation mechanisms, and mitigation mechanisms target different errors, as you can see over here. So it's good to do this sort of characterization. I believe the errors that DRAM is being subjected to is also growing. So at some point, maybe 10 years down the road, we'll write a paper that looks similar to this in DRAM. 10 years ago, maybe the error types were very small, relatively small. And this doesn't even include the soft errors, for example. We don't even deal with soft errors here because soft errors they exist in any technology. Soft errors are basically errors that could happen, for example, due to some particle strike. A neutron strikes your circuit and you get a bit flip. This is just random luck, right? It's not really inherent to the technology. It's really external. And it can happen to anything. It can happen to you also. A particle can strike you and you may be okay, hopefully, if you don't, unless you have some, let's say, safety critical electronic circuitry on you. But basically that's random. So that affects every technology. That's why they're not classified here. Okay, so this is a more up-to-date version of that paper that talks about controllers. There's more work on SSD controllers that we have done. I'm just going to flash these because we're going to cover these at some point. But there are interesting issues that we're going to cover specifically in DRAM to begin with. But just to give you an idea, these issues also exist, like fairness issues, interference issues exist in SSDs. There's also security issues that exist in SSDs. Reducing latency is important in SSDs also. Reliability, temperature, they all affect SSDs. In fact, temperature is a big effect in SSDs. And there are good reasons to actually build SSD architectures to enable parallelism. Like we talked about subarray level parallelism, for example, right? Similar ideas can be applied to SSDs, and you may actually have more freedom in the SSD so that you can access many chips or subarrays, etc., in parallel. Okay, so we have lectures on this that are going to come up. Mohammed may deliver some of them, or Rakesh in the back. They've been working on SSDs. If you're interested in this, you can talk with them. And we also have a SSD course that actually goes into a lot more detail on these issues than we can in this particular course. In this particular course, we'll probably have 1, maybe 2 lectures on storage and SSDs. Okay. Okay, let's jump to DRAM now. Any questions on what I've covered so far? Yes?
So, if you want to build as components DRAM like SSDs, you would want to make sure that the added components don't increase on latency.
Exactly, yes.
Has there been a study of how the latency impact with SSDs when you introduce all that functionality to
No.
SSD?
That's a good question. So different studies actually study the latency impact. So you can actually look at the studies and they talk about how they affect latency. But in SSDs, those latencies may not be as important, right? Because you take microseconds, for example, to access data. And if you add maybe 1 microsecond, it's okay, as long as you hide it in some way, right? So in SSDs, you have a lot more freedom. So a lot of these techniques that are designed for SSDs may not be immediately applicable to DRAM. Yes, but that's a real concern. If DRAM becomes like much harder to control, and you add mechanisms to overcome those scaling issues, latency is always a problem. We will see also in scheduling, latency is a problem when we talk about scheduling. So in DRAM, latency is a lot more critical. Okay, so we've discussed this before, but I want to also remind people that there are a lot of different DRAM types. These DRAM types are there to cater for different types of accesses, different kinds of use cases, etc. For example, low power DRAM, high bandwidth DRAM, I'm going to list them actually over here. These DRAM types have different interfaces optimized for different purposes, right? Commodity is commodity. It's kind of general purpose. It's not really optimized for anything other than capacity. Perhaps capacity is the best thing to say over here. Low power is specifically optimized for low power while keeping capacity as much as possible. High bandwidth is specifically optimized for high bandwidth access, high throughput. And we know that, especially high bandwidth for graphics. This is actually specifically for graphics. And then there's also low latency is optimized for low latency. And we've discussed this, right? It comes at a cost usually. And then there's 3D stacked memories that also provide high bandwidth, not necessarily specifically designed for graphics, that are actually becoming more popular due to machine learning applications and due to their prevalence in GPUs. And then there's more that may come, right? So today, actually, there's a proliferation of DRAM because there are many use cases of computers, and a single DRAM type is not good enough for everything, right? If you actually demand high bandwidth, you cannot get high bandwidth without actually buying, let's say, 3D stack or high bandwidth memory. If you want extremely high capacity, well, you don't want to probably have just high bandwidth memory in your system, right? If you want very low latency, I guess good luck. You have to give your arm to buy one of these low latency DRAMs today. And don't lose all of your arms. I'm not joking. These people actually charge a lot so that you can get low latency memory. But in the end, underlying microarchitecture is really fundamentally the same. So the operation we have seen of DRAM bank, rank, etc., it's really fundamentally the same. The DRAM cells don't change. DRAM subarrays don't change. Internally, the chips are mostly the same. What's really different is really the analog interface that you have and the basically characteristics like 3D stacking, for example. But if you look at the DRAM itself, it's DRAM dies itself, they're similar. So ideally, you'd like to design a flexible memory controller that can support various DRAM types. But this is very tough. as we have discussed in an earlier lecture, right? First of all, this complicates the memory controller in many ways because you need to support multiple types. Difficult to support all types because they all have different characteristics, different latency characteristics, different refresh characteristics, different number of banks, different widths, etc. And then maybe you want to upgrade. Maybe that's difficult to do. But what's really the most difficult part is the analog interface. Essentially, when you actually communicate with these DRAM types, you need to design an analog, actually more accurately, a mixed signal, meaning mixed digital and analog interface that operates at quite high frequencies. For DDR, for example, it's more than 4 gigahertz today, right? It's increasing, so I cannot keep up with it. But basically, this analog interface design is not easy because it's very high frequency design. If you've done any analog or mixed signal design, operating things at low frequency is not easy to begin with. And if you're at high frequencies, like what we're talking about, 2+ gigahertz, it's even more difficult. So getting things reliable at that frequencies is not easy. And also it's extremely costly in terms of area, as we will see soon. Basically, these interfaces, so that they can be reliable, they need to have analog to digital, digital to analog converters, as well as drivers and I/O pads, where you can actually drive these signals out of the chip, right, at the memory controller. So if you look at a single interface to a single DRAM chip, it's actually pretty big, pretty large. And if you think about replicating this for a whole channel, maybe 64 bits, 128 bits, okay, you design one and then replicate it. That's not that bad, right? Hopefully it works. But now, let's say you design LPDDR6, LPDDR5, right? That happens in a lot of SoCs today, for example. But if you want to add, for example, HBM on top of that to the same chip, now you have to redesign completely the analog and mixed signal interface. So it adds to your cost. Probably more than doubles your cost because you also need to figure out where to lay these out on your chip because your chip is in the end limited by the I/O pins, right? Okay, so this is really the difficulty of adding more memory types to the same chip. Does that make sense? And on top of the analog interface, you still need to design the controller. The controller needs to be different for these different types. So as a result, most chips today have a single interface to DRAM, for good or bad. And this interface directly from the memory controller or directly from the processor chip to DRAM minimizes latency, right? So one way of actually thinking about the memory controller is taking the memory controller to a separate chip. This used to be the case, as we mentioned, 18 years ago or so. And AMD was the first one to actually bring the memory controller to its own chip. And then Intel followed suit because that was the right thing to do. With the VLSI integration, you have a lot of logic to use clearly. And bringing the memory controller to the processor chip was a good idea because it cut the latency, right? It's much better than scheduling requests to a separate memory controller chip, and then that memory controller chip scheduling request to a DRAM chip, right, or DRAM module. So basically, latencies to memory actually were reduced one time by bringing the memory controller from another chip to the processor chip. So it's good to think about these. But then the problem is now you cannot connect the processor chip to a different memory controller interface, right? It used to be much more flexible in the past. It's much less flexible today. Now, today, there are interfaces like Compute Express Link, where people are trying to communicate with the outside world with high bandwidth and low latency, in quotations, because it's not clear if that can be low latency. So you can actually be more flexible. Maybe actually you can send a request to memory through the Compute Express Link interface, and that goes to a memory controller chip, like it used to be in the past. But this means that there's still additional latency, right? So you can actually access probably more flexibly different kinds of memory chips right now with the Compute Express Link type of interface, but that leads to higher latency. So it's good to, there's no way around it, I think. Once you go off chip to another chip, and then that other chip does the memory control functions and scheduling, you're going to get more latency. So people may say Compute Express Link will have the same latency as today's DRAM. That's, I think, violating the fundamental laws of physics. I don't know how it can be possible. Because you can actually design a very high bandwidth, low latency interface if you're actually optimizing that interface to a particular DRAM type, right, on the processor. And also the length of the interconnect is just fundamental, right? Okay. Basically, this was actually, you remember our Ramulator paper. So this is the DRAM types in around 2015. Even in 2015, there were a lot of DRAM types. You can see that HBM was just coming around at that time. In 2013, it was introduced. Hybrid memory cube was there. There are also other things that are not as important today, perhaps. But it's good to think about these things. This is from the Ramulator paper, original. And we also seen this picture where we evaluated many different types of memory and their interactions with workloads. So you're already familiar with this. You're already familiar with the new version of Ramulator, and you're already familiar with the study that we have discussed in the past. Now, let me give you some examples of DRAM control logic. So if you look at DRAM control logic, it's actually pretty large, right? This is, for example, according to AMD, this is 2006, the DRAM interface. It's a lot of logic and analog interface. This is, according to Apple, the LPDDR interface. They have 8 memory channels, and they actually occupy a lot of area. This is AMD again. They call it Global Memory Interconnect, which includes the memory controller. A lot of area. This is, again, IBM. This is memory signaling. Again, a lot of area. IBM has a flexible memory interface, actually. So IBM's interface have been more or less CXL-like for many, many years, because they actually, they needed to design these big iron machines. Big iron machines meaning machines with lots of processing and lots of memory. So they couldn't afford basically just having a small amount of memory connected to a small a processor. They need this flexible interface so that they can increase the amount of memory. And this is part of their flexible interface. Even that flexible interface is high frequency, and even that is occupying a lot of area, as you can see. Okay, I could keep going through this, but now you can see that memory controllers actually occupy a lot of area. Any questions? Now let's go through some functions if there are no questions. So there are many functions that memory controller has. Well, specifically DRAM in this case. You need to ensure correct operation of memory. And in DRAM, there's refresh timing, increasingly other stuff like RowHammer. Basically, correct operation requires a lot of things to think about. On top of this, you need to service DRAM requests while obeying timing constraints of DRAM chips. That's part of the correct operation. And there are many timing constraints, as we have seen before, because you need to take into account resource conflicts, bank, bus, channel, rank, minimum write to read delays, etc. We will see more of these. And also, the memory control needs to translate requests to DRAM command sequences. When requests come from different agents like processors, CPUs, GPUs, or DMA engines, direct memory access engines, these requests specify an address, right? The memory, one of the jobs of the memory controller is to make sure you issue the right commands. You break a request down into commands, right? The request doesn't come with activate, precharge, etc. You need to figure out whether you need to activate a row. You need to figure out when you need to precharge a row. You need to figure out which column you access, etc. Right? So all of those are part of the job of the memory controller. So to be able to do that, the memory controller has an important task, which is buffering requests, because usually the requests come at a rate that is faster than the rate of service that can happen from memory, because processors are much faster and DRAM is much slower. As a result, there needs to be buffering in the memory controller to account for that difference. And once you have buffering, you need to decide what request to schedule so that you can get high performance. This requires the memory controller to take into account underlying characteristics like bank conflicts that happen between different requests, row conflicts that happen, row buffer conflicts that happen. Increasingly, depending on the structure of DRAM, it could be the bank group, because there's something that JEDEC introduced, which groups banks into groups. And you could get conflicts at that level also. You could get conflicts at the channel level. You could get conflicts at the rank level. And you really need to take those into account so that you can get high performance. So this requires some reordering some requests, taking into account all of these resources that you're controlling. Okay, on top of this, a good memory controller should manage power and thermals in DRAM so that you don't exceed some temperature. And also so that you don't actually consume unnecessary power, right? Ideally, you would turn off banks or turn off ranks that you're not using, right, at that moment. Maybe you put them in self-refresh mode, even though you may not know exactly, like we've discussed in an earlier lecture. Somebody suggested that don't refresh parts of memory that are not allocated. Great idea, but that information may not be communicated to the memory controller today. But memory controller can say, oh, I haven't used this rank in a long time. I'm going to turn it off, meaning I'm going to put it in self-refresh mode. There's something called self-refresh mode in DRAM, such that I'm going to tell DRAM, self-refresh this rank. I'm not going to touch you for a while. And when I need that rank again, I'm going to send a signal to that rank saying, get out of the self-refresh mode, I need to access you. So these are some tasks that memory can do so that you can save power. But clearly, this is complicating things, right? Okay, so this is what a somewhat modern memory controller looks like. It's not the best picture, but this is a nice, still a not bad picture, I think. There are the DRAM chips over here on the side. There's clearly an electrical signaling that needs to happen, and there's a signaling interface or electrical interface or the mixed signal interface, I would say. This is a DRAM interface, which is not easy to design to begin with. And that's not the subject of this course also. If you really want to learn how these things are designed, you really need to take, I believe, a high-speed I/O circuit course, mixed signal, analog, digital. So it's really actually a beautiful design, but that's not the subject of this course. We're computer architecture. We're assuming that this is done. But again, that's a very important skill. Increasingly few people have that skill in the world. But I think we need that to actually really design good systems. Okay, well, we need all kinds of skills in the world. We don't need only AI engineers or data scientists in the world. Sorry, I had to say this because sometimes people miss this important thing, right? An AI engineer is not going to do that, and that is extremely important, right? Okay, nothing against AI engineers. I'm just saying that not everybody in the world needs to be that. Okay. And machine learning is not going to do that also. They may help, but really there needs to be a great domain expert designing the circuitry really well. Okay, so on the other end, the memory controller interacts with agents. Essentially, this could be CPUs, GPUs, FPGAs, I/O engines, the direct memory access engines. Essentially, a lot of different things can be connected to the memory controller over here. And today, many things are connected, as we will see soon. And these all basically keep injecting requests to the memory controller. The memory controller's task is to actually get those requests, buffer them, and identify where they should go, which rank, which bank, potentially which bank group, depending on essentially the structure of the DRAM. So basically, which row, which column, etc. The memory controller really needs to do that translation. And once that translation is done, there's some queuing. After some point, there needs to be some scheduling mechanism that happens over here, right? Because there may be many requests. And then there's another design decision that's over here that needs to be done. Do you have a single buffer that is used to distribute requests to different banks, different ranks, etc.? Or do you have separate buffers to different banks or bank groups, for example? This is a classic example of static versus dynamic partitioning of buffer space, right? Do you have a single buffer dynamically partitioned across different banks, or do you have different buffers statically partitioned across different banks? And you can imagine different trade-offs over here. If one bank gets a lot of requests, its buffer becomes full, and all of the other banks' buffers may be empty. And that's the downside of static partitioning in general. You cannot utilize the buffers of other banks if you've statically partitioned the buffers. But then the dynamic partitioning of a large buffer may be more complicated, right? So this is a fundamental trade-off between distributing the buffers or partitioning the buffers or having a unified buffer. And we will talk about that when we talk about resource management more. But you can see that there are a lot of decisions you need to make when you design a memory controller. It's not an easy thing. It's a fun thing, but it's not an easy thing. This is our picture of maybe a little bit more simplified picture of a memory controller from a paper that we will cover maybe today, probably not today, depending on the speed. I need to catch my flight too, so we may need to end the lecture a bit earlier today. But this is an example from a multi-core system. You get requests from, let's say, some number of caches, different cores potentially, or different shared caches. And then each bank has a separate request buffer. And there's reordering that may happen. Each bank has a separate scheduler. So you can see that these are partition schedulers, partition buffers. But at some point, because the channel itself is shared across all of these banks, the data bus and the command bus and the address bus are shared across different banks. At some point, you need to have a global scheduler that decides which bank scheduler's request I should take or which refresh I should take. What should I do, basically? There needs to be a global decision at some point. You cannot partition everything completely because in the end, your channel is shared across all of these entities like banks. It's fun, right? A lot of design decisions. I've been designing memory controllers for a long time, and this is one of the hardest parts of the system. Did I tell you the story of Chuck Tacker? Yes? You remember? Or was it in the seminar course? So it was probably in the seminar course. So who knows about Chuck Tacker? If you've taken the seminar course, your hands would be up high. Anybody else who hasn't taken the seminar course? Nobody knows Chuck Tacker? He's a Turing Award winner. Does that help? And he won the Turing Award deservedly, I should say. So it was a deserved Turing Award. But basically, Chuck Tacker is a pioneer in building personal computers. He actually designed these in 1970s, maybe even late 1960s, etc. While he was doing research in the Western Research Lab, etc. Alto system, for example, was one of the first computers. And he designed very complicated systems compared to their time, right? A personal computer. He also designed tablet PC, for example, while he was at Microsoft. And I met him at Microsoft. We actually talked a lot with each other, worked with each other. But I was actually doing a lot of research on memory controllers at the time. And we were publishing papers, like what I'm going to describe also, some of them. And he was at the time very interested in designing emulation platforms, FPGA-based emulation platforms, so they can accelerate simulation, for example, system-level simulation. And one of the tasks he was busy with for a long time was to actually design the DDR3 memory controller for that FPGA platform. And we used to discuss a lot of issues related to that, but he used to complain a lot, saying that memory controller is the worst thing he has designed in his life. Worst thing in the sense that it's the most difficult thing. So he found designing many systems, memory controllers being the worst and most difficult one. And I kind of agree with him. I think this is one of the most difficult parts of a system. And I believe it needs to become more difficult. Meaning, because it's so important that we cannot really just leave it with simple designs, simplistic designs. Okay, so now you know Chuck Tacker. If someone asks you about Chuck Tacker, you can tell me about it. I think he won the Turing Award in 2009. Okay, so basically, one of the tasks of a memory controller is really to schedule requests, right? We're going to look at some scheduling policies. I'm going to start with simple ones. But memory controller buffers requests. It could be a single bank level buffer. It could be a global buffer across banks, etc. It doesn't matter. You need to have a scheduling policy to decide what requests to schedule next. And of course, one of the goals is to make sure that you don't waste bandwidth, right? You don't waste data bus utilization in general. We're going to kind of talk about that later on also in a different way. It's not an easy task because what does wasting data bus utilization mean? Keeping the data bus busy all the time? How do you do that? You have a lot of timing constraints, as we will see. But let's talk about some general scheduling policies, like first come, first serve. It's really not scheduling, in my opinion. You basically take things in a FIFO queue. That's relatively easy. Oldest arriving request first, basically, is another way of thinking about first come, first serve. Most memory schedulers today are variants of first ready, first come, first serve. I'll simplify this a little bit. Basically, the idea is if you schedule the request that hit in the row buffer first, and assuming that you have multiple such requests, you pick the oldest arriving one among them. So it's a prioritization order in the end. This is slightly better because it maximizes the row buffer hit rate, meaning that it tries to maximize the DRAM throughput, at least in a myopic fashion, meaning short-term fashion, right? You're basically optimizing the row buffer locality at the current time. That doesn't mean you're optimizing for row buffer locality that's really important in the future, potentially, okay? It's good to keep that in mind. Current time versus future, these decisions may be different, right? It may be better to proactively open another row buffer and schedule requests that go over there, depending on the criticality, et cetera, of the request, right? Okay, but basically this also gives you an idea of the difficulty of the problem. So scheduling is actually done at the command level, meaning you don't normally schedule things at the request level. You could, but in the end, you have to translate things into commands, right? In some schedulers, actually, they schedule requests at the request level, and then they issue commands so that they don't need to do command level scheduling. But you could do scheduling at the request level as well as command level. But in the end, column commands, read, write, can be prioritized over row commands, activate, pre-charge. And you know these commands by now. And within each group, older commands are prioritized over younger ones. This is a command level formulation of the FRF-CFS policy. Okay, so I think we have seen this sort of picture before, so I'll go through this relatively quickly, but just a review of the DRAM bank operation. You have two-dimensional array of columns and rows, and you have to bring the data to the sense amplifier's row buffer. Initially, this is empty. If the memory controller needs to access row 0, column 0, it needs to activate row 0 first, which takes some time. And then once the data is in the row buffer, the memory controller needs to send a column command, read in this particular case, to read the data out of column 0, which brings the data out of the DRAM chip, right? Okay, now if you have another access that goes to the same row buffer, this is a row buffer hit because row buffer is ready. Well, no row buffer has row 0, which is what we're trying to access. Of course, the memory controller needs to have some metadata to keep track of which row is open at each bank for correctness purposes, not just for performance purposes, but for correctness purposes. Because if somebody is accessing row 1 again, for example, then you need to write back row 0 or pre-charge the array. So in this case, it's a row buffer hit. The memory controller needs to have logic to determine that. And then the memory controller needs to send column address to get the data out from column 1 in this case. This is again a read request. And then if the processor or one of the CPUs accesses row 0, column 85, the memory controller again realizes that this is a hit. And then it sends the column address, gets the data out. So the memory controller job is to ensure that this works correctly and maybe also to optimize for row buffer locality. Now, if the access that's coming to the memory controller, maybe in the queue, is to row 1, column 0, then the memory controller should realize that row 1 is not open in this bank. I'm assuming that all of these accesses are to the same bank, of course, right? This is a row buffer conflict, and the memory controller needs to first pre-charge the array, which you know what that is by now, right? Basically, it's make sure that the sense amplifier becomes set to VDD over 2 on both ends, and it gets disabled, and also the bit lines. And it sends an activate command to row address 1, which brings the data into the sense amplifier's row buffer, and then the memory controller can send the column address. So clearly, this took a much longer time now. A row buffer conflict took a much longer time than a row buffer hit. As a result, if you want to actually maximize throughput that's coming out of DRAM, you'd better optimize for row buffer locality, right? Maximize the hits that go into your row buffer. Okay, so we'll see this more, but that's one of the constraints. But in the end, a scheduling policy is really a request prioritization order. I'm not going to cover every scheduling policy today, but just to give you ideas, like prioritization can be based on the age of the request or arrival time, row buffer hit or miss status, request type. If you know that information, maybe you treat read requests differently from write requests. Actually, you have to in DRAM. DRAM read requests and DRAM write requests are different because they do different actions to the memory bus channel, essentially. You cannot schedule a read while you're scheduling writes, because when you're actually writing, you're really pushing data from one side of the memory bus to the other direction. When you're reading, the direction of the bus needs to be turned around. And this is called bus turnaround time. Unfortunately, there's no way to read and write at the same time concurrently through the bus. You have to switch the bus direction. And this introduces the delays. This introduces special delays like T write to read, T read to write. Now you can see there's another scheduling decision we need to make, right? It's not just about the row buffer. Row buffer is easy. Well, easy. But if you now you're adding another dimension. I cannot schedule writes at the same time I can schedule reads. So how do I handle this thing? Writes, we know that are not as important because you're really writing to DRAM and hopefully the processor is not waiting for it. Reads, on the other hand, could be critical because the processor may be actually immediately waiting for it. But now, what happens if my write buffer gets full? If my write buffer is full, I have to push these writes out to DRAM. Otherwise, where am I going to put the next write? Right? So you need to switch to a mode where the memory controller does writes for a while. While the memory controller is doing writes for a while on that channel, it cannot do reads. Meaning now you're delaying reads that are supposed to be more critical because you have to do writes. So meaning that writes are critical also at that point, right? So this is actually the design choices that you need to make when you actually design a memory controller. One of the design choices, of course. And then if you have this information, what about prefetches, right? This is not something that the processor needs immediately, but the prefetcher generated the request and they tagged it, if you're lucky. They tagged the request saying that I want to prefetch from this location. And this is a hint to the memory controller saying that this may not be as important. How do you deal with that? Right? Do you prioritize prefetches over writes? Do you ever prioritize prefetches over reads? It's good to think about. We actually have papers on that topic called prefetch over DRAM controllers. And sometimes actually prioritizing prefetches over reads is a good idea, especially if you're exploiting row buffer locality with those prefetches. You don't want that prefetch to cause a bank conflict later on. You actually schedule the prefetches that go to a row buffer that's open and get them out quickly, as instead of and maybe delay some reads that you know are actually demand reads, as opposed to letting those prefetches, let's say, be not serviced for a while, service this read that will close the row, which will take time, and then service the prefetch that will close the row and open it again. So as opposed to causing more bank conflicts, you may actually be better off not causing the bank conflicts, but prioritizing a prefetch request, for example. So it's good to think about these decisions. And hopefully where I'm building up to is, I think making a lot of these decisions with a lot of timing constraints is not easy as a human. As a result, the scheduling policies that we will see are going to be relatively simple and heuristic based, and they may not work under all conditions. Even though you can actually generate a lot of insight as to why some policies may work, putting everything together is not easy. Okay, so, and then there could be a requester type. If you're lucky, you may have this information also. Is this read request coming from a store miss, meaning the processor needs to store to a location and it's missed in the cache, and that cache block needs to be brought to the caches from the memory? Or does it belong to a load miss, meaning the processor is actually trying to read from that location so that it can actually execute something that's dependent on that read? These are two different criticalities, right? A store miss may not be that critical to the processor because the processor, that store instruction may not have any dependent instructions. Well, of course, a load may depend on a store, but that may be farther down in the instruction tree. Whereas a load miss may be immediately critical because the data that's needed by the load may be needed by an add instruction afterwards, right? A branch instruction, etc. So if you have this information, how do you prioritize requests? Probably I would prioritize a load miss without any other information, right? Request criticality. This is actually something that we've been kind of talking about, but maybe there are other dimensions of criticality, right? How long is this request going to store? How long is this request going to stall the processor? Will it stall the processor only one cycle because the request is actually the latency of the request will be overlapped with other requests? Or will it stall the processor for 100 cycles because the latency is not overlapped by any other request? This is the only request that the processor is waiting for, right? So this criticality is an interesting thing, actually. And how do you approximate it, measure it, is actually not an easy thing. Later, we may talk about criticality, but today we're not going to go into that much. And people have talked about different ways of thinking about criticality. I don't think we have a very good way at this point, or at least a perfect way. So basically, is it the oldest miss in the core? How many instructions in the core are dependent on it? Will it stall the processor? These are all good questions to ask. And you can make it, will it stall the processor in the end is a good measure, but can you guess that easily is another question. Okay, and then there's interference cost to other cores. So we've talked about all of these things from a processor perspective, but then what else do you do? What damage is this request going to do to the performance of other agents that are trying to access memory? If I actually prioritize this request from thread A over another request from thread B to the same bank, I'm going to delay the request of thread B. Maybe thread B is more critical from user perspective. Maybe it needs to be prioritized for other reasons, basically. This is also something that the memory controller needs to think about. And if you don't think about it, as we will see later on, you run into problems like denial of service and fairness. And there are many, many other things. This is, I think, a good quick summary of what prioritization could be based on. There's also, I think there's room for creativity over here. People need to think about other things that prioritization could be based on. Any questions? Yeah.
Nodes and stores where have a lot of branch instructions nearby.
Yeah.
Say you take a specific branch, but that node and store is not useful anymore.
Yeah.
Communicate the information as well. You have a branch instruction in the future.
Yeah.
So don't try that.
Yeah. Now you're actually making things more complicated, right? Potentially, yes. Potentially, you could tag. That's one way of also thinking about criticality or non-criticality, right? If the branch instructions depend on a load, for example, this may be good to communicate, because if that branch, assuming that branch is highly mispredicted, this causes a problem, right? Because that's really potentially that's a very highly critical branch. And that's because the branch is very highly critical, probably the load is also highly critical. But if the branch is predicted correctly, maybe you don't care, right? Yeah, so it's good to think about these things. There's no perfect answer, unfortunately. Maybe you can talk to Rahul about that. He's going to come up with the best mechanism to predict criticality soon. And hopefully use it in the memory controllers, but other parts of the system too. If you can really understand the criticality of instructions, then you can really design much better resource management policies, right? Because criticality of an instruction, assuming you quantified it correctly, then that instruction needs to really be prioritized everywhere, right? It needs to be prioritized in the processor, caches, memory controller, storage, wherever it really touches at that point. The problem is that criticality is difficult to identify first, and that criticality is dynamic. It changes over time. If you prioritize this, next time maybe it may not be critical. That's one thing. But once you prioritize it, maybe something else becomes critical, right? So there are multiple things that become critical close to each other potentially as well. Okay, well, these are good thoughts. Okay, let me cover row buffer management policies relatively quickly, because we talked about that. Even this is actually, so I gave you a lot of dimensions in memory controller, not everything. We'll see a little bit more, but we're not going to cover everything. But even row buffer management policies are subject to optimization. So there are usually three major policies. One is keeping the row open after an access. That's called the open row policy. Now, this is good if the next access to the same bank needs the same row. That's a row hit. This is bad if the next access might need a different row, right? This is a row conflict, wasted energy, right? If that's the case, you could have been better off with a closed row policy, which says that close the row after you access the row, unless there are other requests already in the request buffer that need the same row. That's a not so dumb closed row policy, right? If you always close the row, that's kind of dumb, right? Knowing that there are other requests that are waiting for this row there, yeah, then you're shooting yourself in the foot, probably as a memory controller. But if you look at your queue and say, oh, there's no other request waiting, maybe I should close the row so that someone else can access it. Then if the next access needs a different row, you avoid a row conflict. That's good. But if the next access might need the same row, you get an extra activation latency, right? And there's no perfect choice over here, unfortunately, unless you predict the future somehow. And that's what a lot of controllers do. They use adaptive policies. They try to predict whether or not the next access to the bank will be to the same row and act accordingly. And how do you design that predictor is not easy. There could be different policies. Maybe there could be machine learning employed here. But this is only one aspect of the memory controller, as you can see, right? Row buffer management. It's an important aspect, but it's only one aspect. Clearly, this integrates also with the scheduling policy that you have in the memory controller, right? Do you actually exploit row buffer locality as much as possible? That would be useful in general in memory controllers to exploit the row buffer locality. Okay, maybe one more thing over here is there could be, I mean, these policies actually don't need to be just in the memory controller, right? You could imagine a last level cache policy that's aware of the row buffer. And last level cache, when it's evicting a cache block, it says, oh, this cache block, I have a bunch of potential victim candidates that I'm going to evict. I'm going to choose the one that is going to maximize the row buffer locality downstream, given the information I have about the status of the row buffer right now. And if you actually have that communication between the memory controller and the last level cache, then you could potentially co-optimize row buffer locality. But of course, this may not be the best decision for a cache eviction. but usually there's some slack in eviction that you need to do. So this is a mechanism that we propose that I'm going to talk about very briefly in the paper that I'll mention soon. Okay, this is just a table that shows what happens if you have a given policy, and this is your first access, and this is your next access. These are the commands needed for next access. I'm not going to go through this table. You can study it on your own. There's nothing new here that's different from what I just said over here. It just quantifies some things or makes things more concrete by telling you which commands are needed for the second access, assuming you have a row policy and first access and second access. Okay, let's talk about power management very quickly. I'm going to take a break at a clean point. As I said, DRAM chips have power modes. The idea here in general is to power down a chip or a portion of it, if you have the capability, when not accessing it. These are, unfortunately, this is an area that's, in my opinion, not very well studied. But I think this will become more important, especially with 3D stacking of DRAM. Yesterday, we were talking about DRAM being stacked on top of processors in SoCs, right? And this will really impact the power consumption as well as temperature. Temperature and power consumption are quite related things, right? There's a direct relationship between temperature and power consumption. We need to really manage the power much better in DRAM going into the future. But these are some power states that exist in the DRAM chip. So active is basically, you're really active, meaning the row buffer is active. Well, there's something that's accessing. Basically, when you're accessing, that's when you consume the highest power. But it's not a power state itself. It's really a state of what's happening at that point. Active is the highest power state. The row buffer is active and it's connected and it's basically wasting power at that time. Idling a particular bank could be one, assuming your chip supports it, meaning you close the row and it's idle. Maybe you do some power management in the bank. All banks idle. That also closes all of the rows, and maybe it actually has some power management. It reduces the power supply, etc. It could reduce the voltage, etc. Right? And then there's a power down state, and then there's self-refresh, which is the lowest power. Self-refresh I mentioned, right? Basically, you turn off as much as possible, except for the refresh circuitry, internal refresh circuitry, and you set the internal refresh circuitry such that the DRAM independently, without requiring the memory controller to send refresh commands, DRAM by itself refreshes itself. Right? That's the lowest power mode. Even then, it's clearly consuming some power, right? Because there needs to be some circuitry that is turned on, and there needs to be refreshes that happen periodically. Okay, so the trade-off is that when you transition between one state to another, low power to high power or high power to low power, you incur latency, during which the chip cannot be accessed. This is kind of dead time, where you need to transition the power state. This clearly has an impact on performance. So if you're optimizing for power, you need to be careful, right? When should I put the DRAM into self-refresh state, right? When this is kind of a prediction mechanism again, right? For example, I'm not using my phone right now. It'd better be in self-refresh mode. But when I use my phone, maybe self-refresh mode is not that great because you need to get out of that quickly, right? So other states also have, and going into the self-refresh mode and getting out of the self-refresh mode actually has the highest penalty in terms of latency. But other states also have penalties. So this is not an easy optimization problem, and there are papers on this topic. But I believe the power states in DRAM needs to be re-examined also. Okay, so this is a much clean and nice point. Today I'm going to take a shorter break because we're going to end early. Let's take a break until 14:20, 10 minutes, and then we'll be back with more DRAM control. Okay, I think it's time to get started. Okay, now that we've covered some basics, let's talk about the difficulty of DRAM control. I think I've given a lot of this, but essentially, we need to obey many DRAM timing constraints for correctness. We're going to see a little bit more of these. And it turns out there, 50 is actually an understatement, more than 100 timing constraints in modern DRAM. This is because of the way interface is designed, right? Interface is designed so that memory controller can know everything about the timing of DRAM so that you can actually control it in a fashion that's relatively optimized. As we have seen in the last lecture, it's not very optimized. All of these timing parameters are worst case parameters, but there are many timing parameters which makes it still better than having a single timing parameter that's the worst case across all of those timing parameters. Meaning you could have one timing parameter that is the worst possible timing parameter and say, after every request I make, I'm going to wait that longest timing parameter, right? That's very bad. So that's why people have come to this interface where you have so many timing parameters for different fine-grained actions, and the memory controller needs to be aware of those timing parameters so that you avoid this huge, long, even longer timing parameter. Does that make sense? So this is a conscious design choice in synchronous DRAM where the memory controller is in complete control and it needs to schedule all of these requests based on the timing parameters. As I mentioned, there's a T write to read delay, which is the minimum number of cycles to wait before issuing a read command after a write command is issued. So you cannot do reads and writes concurrently, except for some overlapping conditions, which I'm not going to go into. TRC, you already know, this is the row cycling time, which is really what latency is usually measured as, but it's not the only latency measure, clearly, as you know. This is the minimum number of cycles between the issuing of 2 consecutive activate commands to the same egg. It's really the row conflict time. It's called row cycling, but it's also row conflict time, kind of. Okay, there's other timing constraints, as we will see in a little bit, but it's a lot to optimize for within these constraints. Then you need to keep track of many resources, as we have discussed, and there are many resources. These are increasing over time. Bank groups are not here, but they were introduced relatively recently, for example. You need to handle DRAM refresh, clearly, and we've spent one full lecture on that topic. You need to manage power consumption, as we have discussed briefly. You need to optimize performance and quality of service in the presence of all of these constraints. And you need to design things, like design of a controller, the hardware itself. To do reordering is not simple. Even something like reordering is not that simple in the end. Because to be able to do reordering, you need to figure out what to reorder, and you need to also do some matching of requests, which makes the hardware more complicated. And once you actually add other constraints like fairness and quality of service, as we will discuss either at the end of this lecture or at a later lecture, this really complicates the scheduling problem. And we're not really considering a whole lot of other things over here, like energy, for example. Well, power is over there, but maybe there's also other optimizations that you can do for energy. Okay, so this is the paper that I mentioned that basically proposes to make the last level cache aware of the characteristics of DRAM so that you can schedule write-backs from the cache in a way that really doesn't hurt performance, or in a way that exploits a robot for locality in DRAM. So this paper, well, this is the paper reference over here. It's a technical report. It was never published, but it's actually a pretty interesting paper, I think. It basically shows how to schedule writes and reads in DRAM. And this is some of the timing parameters over here from that paper. If you're interested, you can take a look. More recently, we've written papers that actually clarify the timing parameters. One way of learning about timing parameters is to go and read DRAM data sheets, which is not bad, but those are actually terrible for understanding and insight in general. They don't tell you why they make the design decisions they make. So it's better to actually read papers that are written with insight as a first-class constraint, right? In data sheets, insight is not the first-class constraint. That's not the goal. It's really to tell the memory controller designer, this is what you need to do. Don't ask me why. This is why. This is what you need to do. But good papers usually don't tell you what. In fact, they almost always tell you why before they tell you what, right? That's why when you're writing a good paper, you should not focus on what first. You should really focus on why first. What is your goal? Why are you making design decisions you're making? in the end, I don't really care about the designs you're making if you're not justifying those design decisions very well, right? And there are good reasons for these timing parameters, right? These are actually, these two papers, I think, explain the reasoning reasonably well. And these are papers that we've discussed, the SALP paper and tiered latency DRAM paper. And they actually show what is the scope of the timing parameters, etc. I'm going to talk about some of these in a little bit, but let's take a look at why these exist. This is also a picture that you have seen yesterday when we talk about true random number generation in DRAM, right? Basically, these timing constraints exist because you need to give enough time to the circuit to settle, right? That's part of the reason for the timing constraints. You activate, and after activation, the cell starts sharing its charge with the bit line. You can see it was 0.5 VDD, the bit line voltage. Cell is charged, so the bit line voltage is perturbed to the higher state. And at some point, the sense amplifier gets enabled. This is not controlled by the memory controller today, as we have discussed with the Codic paper yesterday, right? The sense amplifier enabling happens internally. There's an internal timing circuitry that actually kicks in the sense amplifier. And then the sense amplifier amplifies the bit line voltage to the highest possible. And then at some point, you can do a read. And this read timing constraint is determined so that you don't get the wrong data when you read. That's the idea basically of a timing constraint. And this is called TRCD, activate to read delay, in other words. As we have discussed, you could actually pull this earlier because this cell may have a ready to access voltage level that's reliable much earlier than the TRCD timing constraint. But we add a guard band for various reasons we've discussed again yesterday: temperature variation, spatial variation, dynamic variation, etc., to protect, to get the correct result while having a single timing parameter, right? So, and you have also seen yesterday that different cells behave differently. So I should probably animate. Well, it doesn't animate. There are strong cells that could be accessed earlier. There are weak cells that actually eat into this guard band. Hopefully they don't actually go out of the guard band, etc. Okay, so there's a reason for these timing constraints, as you can see, to make sure that the circuits settle and they give you the correct result after you take an action. Clearly, there are other timing constraints that we're not going to go into, but this SALP paper, subarray level parallelism paper, actually does a nice job, I think, describing it, at least a major set of the timing parameters, by also showing pictures of what happens over here. So there's some timing constraints that are actually at the bank level, like what we have seen. TRCDs at the bank level. It's between activate and read and write commands. And this is the value in a particular standard, DDR3 standard. Let's see, what should I pick? T write. This is the, after doing a write, you need to do a pre-charge. I need to wait for some time so that the data is actually guaranteed to be written, including the guard band that's added. In this particular case, it's 15 nanoseconds, for example. There's a rank level timing constraint, read to write. This is actually not necessarily specified this way in the standard. And we say basically not explicitly specified by the JEDEC standard, as you can see. So there are no, but I think intuitively, insightfully, it's a read to write timing constraint. You need to obey this as a function of other timing constraints. But I think intuitively, it's good to think about it as a read to write timing constraint. Basically, this is how long you need to wait before you issue a write command after you issue the read command. It's a rank level, meaning you need to enforce it at the rank level. To any bank, you cannot issue a write after you issue the read unless you wait for this long. And this long is, in the standard, it's 11 to 15 nanoseconds, as you can see. It's the other way around also exists, which is write to read, as we have discussed, right? And there are also interesting idiosyncrasies. For example, we say this is the delay between the write command and the read command, but it's not really the command. There's a star over here, asterisk, that you need to read. It goes into effect after the last write data, not from the write command. Because you send the write command and you send a burst of data, and you should really make sure that you schedule the read command n nanoseconds or TWTR nanoseconds after you sent the last piece of data to DRAM. So you need to really know all of these to design the memory control. If you make a mistake, then you can get a wrong data value. You can get data corruption. Yes?
Are these timing constraints different from DIM to DIM? And if yes, how does the
Yeah, that's a great question. It could be different. Data sheets usually specify a variety or a range of timing parameters. They don't dictate. Usually these timing parameters are read when the memory controller initializes. You read something called SPD circuitry in DRAM, and you get the timings that are employed by that particular module. Yeah. So it could be changed as you suggest. But there's a range that's usually specified in the data sheets. Under different conditions also, under different voltages, these may change also. Basically, for different voltages, different temperatures, there are different timing parameters. Yes?
When you say show command, we need the moment when the memory controller sends the command to the...
That's correct, yes. Mm-hmm. Yeah. It's all from the memory controller's perspective. Because in all of these, DRAM is a dumb agent. It basically can do nothing other than to obey the command. Yeah. No, no, it doesn't exist. The assumption is that it's completely reliable. Yeah, but there could be, I mean, in really extreme scenarios, there's an alert signal that could be raised by a DRAM chip that says something wrong has happened with me. Exactly, for writes you don't necessarily know. Yeah, there's no acknowledgement, so. Yeah, but we're going to talk about some of that soon. Maybe there should be a better. So the assumption is that basically the memory handles all of that and it doesn't need to acknowledge. This also reduces the protocol overhead in a sense, right? If there were acknowledgements that you need to wait, the protocol overhead would be high. And acknowledgements are useful in unreliable medium, of course. The assumption here is it's reliable mostly, hopefully. So you can see that it's not designed for complete robustness. Atabak, do you have anything to add about the about the alert command? No? Do you know when it's used, how it's used? Mm-hmm. Yes. Mm-hmm. 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 Yes. So that's basically the level of kind of negative acknowledgement. But it's not clear when you receive the alert, right? It may be a bit too late. You may have actually proceeded a lot, right? Mm-hmm. Yeah. Yeah, so the protocol is really not fully optimized for robustness, I think. It just assumes things are done. And yeah, okay. We can talk more about that later on. There may be errors happening at different places, basically, where alert may not be able to catch those errors, right? But these are good things to think about. How do you design a better protocol? Okay, what else do I want to say over here? There are also channel level constraints that I'm not going to get into there. For example, here, TCCD is between any read command or write command that needs to be enforced at the channel level. Yeah. This is not a comprehensive set, but I think this is an insightful way of thinking about commands. Okay, and there's another explanation, the other paper that I'm not going to go into. But basically, I think my point so far is DRAM controller design is actually becoming more difficult. It's going to become more and more difficult. If you look at an SoC today, all of the processors go through a DRAM controller. And we're going to expand this DRAM controller to other memory controller, like hybrid memory controllers later on when we talk about emerging technologies. But we've seen examples of hybrid memory controllers also. So essentially, you have heterogeneous agents accessing main memory. There's interference happening between them. And the memory controller needs to do everything that we said, plus managing those interference. As a result, there are many goals that you need to satisfy at the same time: performance, fairness, quality of service, energy efficiency, power, and who knows what else. Maybe you'll come up with some other metrics. So we will see some more of this also. So one of the things that, like going back to the conversation we were discussing while I was at Microsoft with Chuck Tacker, one of the things that we were working on at the same time, Chuck Tacker was complaining about how DRAM controllers being the worst thing he's designed in his life, was actually to make the design easier for people of memory controllers. And I like this work. This is one of the relatively early applications of reinforcement learning to hardware design. And I think there needs to be more and more and more of this sort of approach that hopefully make things more robust and also easier to optimize as well. So I'm going to describe this a little bit. This appeared in ISCA in 2008. It will be one of your readings, as you can see. But the idea is, it's really difficult to design a policy that maximizes performance. We're going to focus only on performance here. But then there are other metrics, don't forget. There are too many things about. Thanks, Rahul. Too many things to think about. Is this you? No, okay. you just found it somewhere? Okay. Rahul enhanced my boring slides with pictures like this. It's Jackie Chan, really? Okay, it's a meme, okay. And why is he doing that? He's frustrated about memory controllers, apparently. I think Jackie Chan would break the memory controllers if he saw them. Okay, but basically there are too many things to think about, and there's continuously changing workload and system behavior too, right? You may actually design a policy that is heuristic based, that works for some workloads or some system behavior, but that may not work very well for some other workloads, right? When do you switch between read to write mode, for example? Do you use a high watermark, meaning if 80% of your write buffer is full, you start servicing writes? Is that a good threshold? Is that graceful? Usually that sort of hard thresholds are not very graceful, right? There are workloads that actually abuse in the sense that they don't know necessarily the threshold, but they actually send a lot of requests, and now your threshold is actually bad for some workload and good for some other workload potentially, right? So it's very hard to design things such that you can really take into account changing behavior of different workloads, and there are many workloads. If you can imagine some legal action happening to DRAM, it happens in real workloads. Real workloads are so varied and complicated that they actually do things that you may never think are done. It could be done. For example, I think I'll go back to the comment we received with RowHammer paper, right? RowHammer paper, show this on real workloads, right? That was one of the comments, and that was one of the reasons for rejection. We couldn't show it for real workloads. I mean, we could have, I guess. That's a lot of work. But RowHammer bit flips happen in real workloads. People found them, actually. But maybe the natural tendency is not expect that this would happen. So real workloads do a lot of things, basically. So it's very hard to optimize for everything that's done by real workloads. Software is so, if you think hardware is complicated, software is orders of magnitude more complicated. There are a whole lot more people writing software. There's all kinds of software, and it all executes on these systems. So it's very hard to optimize for everything. So basically the dream is that given these, wouldn't it be nice if the hardware designer didn't need to optimize for everything? Basically, figure out a way of designing a memory controller such that it automatically finds a good scheduling policy on its own. In this case, we're only concerned with a scheduling policy to optimize performance. But this could be extended. So basically, we're going to optimize for the performance function. Memory controller sits in between cores and memory. And our goal is to resolve memory contention by scheduling requests. So how do we schedule requests to maximize system performance? So I think I already said a lot of these. And the idea, the general idea is to really use machine learning. Have an online machine learning policy that keeps updated while the memory controller is running, while the system is running, while the workload is changing, while the system is changing, potentially, right? That's the idea. And we found out, for reasons that are given in the paper, if you read the paper, I think there's a beautiful mapping of reinforcement learning to memory control. Especially reinforcement learning works nicely if the problem you're optimizing is the Markov decision process. And we motivate that in this particular case, the memory scheduling problem is a Markov decision process. And you can see that I'm not going to go into that right now. We're going to see Markov decision processes later a little bit when we talk about prefetching also. We'll go into it a little bit more detail, but you can read the paper. Essentially, the design that we have is to use a reinforcement learning agent built in hardware is as the memory controller. Then the question is, of course, how do you design that thing? Okay. And reinforcement learning is nice because it's essentially you learn by getting reinforced positively or negatively after you take an action, right? Meaning at a given state, you take an action and you over time observe whether that action was good for performance or bad for performance. And over time, you collect a reward value for that action that you've taken in that given state. So over time, you learn to associate state action pairs that lead to high rewards, assuming you've set up the system and the reward function right. And when you see the same state next time, and when you see available actions, you pick the action that leads to the highest expected reward based on what you've seen. If that doesn't lead to a reward again, over time you get reinforced and you start, let's say, learning something else. Right? So it's very adaptive. Based on the rewards you've seen, based on the actions you've taken at given states, over time you change your policy. There's no reason to actually keep the same policy. You don't necessarily keep the same policy. You basically adapt over time. So it's very much more adaptive than existing policies. Remember the existing policies that we've discussed, FRF-CFS, for example. Pick the request that hits in the row buffer first, and then have also a write scheduling policy that's we kind of discussed as well. This is much more adaptive. So hopefully this dynamically and continuously learns and employs the best scheduling policy to maximize long-term performance. So I think I've said this, but reinforcement learning is essentially one of the fundamental learning-based mechanisms. Sometimes it's forgotten, but at least there's, I guess, the Nobel Prize went to AlphaFold, which is essentially a deep reinforcement learning agent to discover the structure of proteins, right? And I think this was a pretty good discovery. So reinforcement learning is actually employed. Do you agree? In existing systems for protein discovery. Yeah, Alpha what? AlphaGo, yes. What thing?
The game solver kind of.
Okay, so yeah, AlphaGo is the game for it. There's so many alphas. Did it receive the Nobel Prize also? Okay, why not a Nobel Prize in gaming also? I think gamers would be happy. But these are really related to each other, AlphaGo and AlphaFold?
Coming from the same group.
Okay, I see. Okay.
It's a state of the art in a sense that what the IBM Blue Gene did to chess is what AlphaGo did to Go.
Yes.
It will be huge state space that we are seeing in the environment. So it can navigate autonomously, knowing the best and go on against the best code in the world.
Yeah, and that's also deep reinforcement learning. Yes. Yes. In this case, what we did was not deep reinforcement learning. This is before the time of, let's say, deep learning became popular. Ours is a little bit table-based classical reinforcement learning, which I think still has a lot of applicability in hardware, especially when you need to make timing critical decisions, right? Okay, so the basic idea is reinforcement learning is a fundamental learning technique. Actually, it was developed not before computer science. It's really developed as a way of explaining how organisms learn, like humans, dogs, animals, etc. They interact with the environment because they're agents. They observe the state of the environment and take an action. And over time, if they get a reward given a particular state and action pair, they keep learning that reward. They keep associating that reward with a state action pair, and they keep getting reinforced and keep essentially taking the same action at the same state, right? That's how Ivan Pavlov associated the ring of a bell with the food, and the dogs started drooling whenever they heard the ring of a bell, even when they didn't get the food after some point, right? So that's reinforcement learning for you. It's very strong, and some people actually think that this is the only, I think these are extremes, but for example, Skinner, B.F. Skinner, he's a very famous American psychologist, and he's actually quite brilliant. Well, he was quite brilliant, but he actually trained pigeons to deliver messages in Second World War purely based on reinforcement learning principles. And according to him, everything in the world was reinforcement learning, nothing else. Reinforcement learning. I think it's extreme, but I think you need some extreme views to actually advance the state of the art in science. Because a lot of people, I think right now, may not think that reinforcement learning is interesting. But I think there's actually a lot of value to reinforcement learning. Okay, but basically applying this concept to a hardware scheduler like the memory controller, this scheduler can be thought of as an agent that observes the state of the system. And this could be anything in the system, actually, whatever you feed to the scheduler, to this agent. And it takes an action, which is essentially scheduling a command, which could be a no-op action also. And then based on that action, it observes the performance impact of the action, which is data bus utilization in this case. We're going to use data bus utilization as a good performance measure. You get a reward if you actually utilize the data bus. And over time, you try to associate state action pairs with these data bus Q values or expected data bus utilizations. But this is also not short term. You don't look at only the data bus utilization that you got based on the action you've taken in the state immediately, but you also look at what happened in the past. So your reward function is weighted based on the impact of your decision over time. So you may actually get the data bus utilized 3 cycles later. Your reward function gets affected by that, right? This enables you to actually optimize for a longer term reward, as opposed to, if you don't get an immediate reward right now, it may be okay. If you get rewards 10 cycles after that, all of your data bus cycles are utilized. This may be indicative potentially of what you've done 10 cycles ago, right? So there needs to be some design choices that need to be made like this. So this is why this is a longer term optimization. Okay, so you got the idea. Without going into a lot of detail, you'll read the paper, I think. The agent learns to associate system states and actions, commands in this case, with a long-term reward values. Each action at a given state leads to a learned reward. And at a given time, the agent schedules the command with the highest estimated long-term reward value for a given state. And it continuously updates the reward values for state action pairs based on continuous feedback from the system. So it's a very dynamic scheduling policy, as you can see. And the paper describes it in more detail. But basically, a state, you can observe the state of the transaction queue. You can observe the state potentially of other things, but we didn't do that. Potentially anything in the system could be observed, right? The processors. Actually, we actually have information about the processors embedded into the transaction queue, as you will see. And then you take an action and you get a reward. There could be different reward functions. To summarize, actions are relatively easy, but you still need to be careful. So these are some actions that you have, but we distinguish, for example, read based on a load miss and read based on a store miss. We found out it's important to distinguish between them. We also have a preemptive precharge command. Precharge pending is basically you need to precharge it to schedule a request. You need to precharge a bank to schedule a request. Whereas preemptive precharge is a command that you can issue even though there's no request that actually tries to access that bank. The reason to have this command is to give the memory controller the possibility to learn preemptive precharge. Why? Because if somehow the reinforcement learning mechanism figures this out, it can quickly precharge things so that it doesn't have to do the precharge on the critical path, right, of a request. And then there's a no-op. Basically, this is also important. Essentially, the memory controller can issue a no-op if it somehow learns that issuing a no-op is better than issuing a command, right? And this is possible. If you don't do anything, maybe there are 2 options, for example, right? You don't do anything versus you do something to close the row that's currently open. Maybe not doing anything is better because you're going to get some other request soon to that row that is currently open, right? If you didn't have the no-op action, then you have to choose another action, which may be closing the row, right? So it's important to design the actions carefully also, and there are good reasons why they're put over here. And then there's the state attributes, which is one of the hardest parts. Actually, the hardest part is really the reward function in the end. But in this case, we made it easy because we're assuming that whenever we schedule read and write commands, we get a +1 positive reward. Otherwise, we get a non-negative 0 reward, essentially. The goal is to maximize long-term data bus utilization. That was our goal, but this may not be the best goal, right? If you are trying to provide quality of service, for example, to different threads. But our goal was we're running parallel applications. And maximizing data bus utilization is hopefully a good correlator for performance. It's not necessary even with parallel applications, but it's not a bad metric. We didn't want to deal with more complicated reward functions yet. Our goal was to really show that with this reward function, we get benefits. State attributes is really what you could imagine. In this paper, we imagined 200+ different state attributes. And we basically did feature selection through a lot of simulations to figure out which state attributes are good things to consider when making this scheduling decision. And we found out some things that are interesting, right? Number of reads, writes, and load misses in the transaction queue, for example. Number of pending writes for a reference row. This is something that memory controllers that they don't normally reference row. And we found out that this is actually a good metric to use as part of the state attributes to make a decision, because this may actually enable you to prioritize doing something to that row, maybe keeping it open, for example, right? And also a number of reorder buffer heads. Reorder buffer is the instruction ordering structure in each core, and the oldest instruction is referred to as reorder buffer head. And basically, this counts the number of oldest instructions in each core that are waiting for the reference row. So if 4 cores are waiting for the reference row, that row is probably important. And this indicates that maybe you should do something special in your scheduling for that row. If 0 is the number that's waiting for that row, maybe that row is not that important. Again, we're reasoning about these because these are selected based on feature selection. We're not designing a policy that uses this information. The policy itself is dynamically found by a reinforcement learning agent based on reinforcement learning principles. And the exact policy is something that we cannot know. Actually, you know exactly per the given instance what the decision tree may be. You can actually lay out all of those weights, etc., as a decision tree. But this policy keeps changing. So this is a policy that you cannot design, in a sense, as a human, right? Like this, I don't know how to design as a human. And I don't know a human who could design as a human. That's why this is learning in a different way, right? Okay, so, but we know that this policy somehow makes use of this information to take better actions, as you will see, than... In fact, what we did was, after doing the feature selection, after figuring out that these are useful things, we tried to design a policy that uses all of this information, and you can see that in the paper. We came up with some prioritization order that takes into account all of these state attributes that we found are important for our reinforcement learning agent. Then we came up with a static policy designed by a human. So this is where feature selection is aiding the human designer. And we found out that our policy is better than existing policies, but still much worse than a reinforcement learning agent making use of the same information. Exact same information. And in that sense, that's the most fair comparison that you can get, right? You're comparing exactly the same information exposed to a human who is hopefully a domain expert. And that human uses the same state attributes to design a policy as best as they can. And you get some performance. And the reinforcement learning agent, non-human, hardware, uses exactly the same information to design a policy that's completely different. And hardware wins in this case. Maybe not as much as AlphaGo that Rahul is very excited about, but still, I think this is a tough problem also. Okay. Okay, there's also the request relative reorder buffer order, which is basically potentially how important the request is compared to other things in the instruction window. Okay, so I think I've covered all of these. How do you actually design the hardware is something that I'm not going to cover. That's also important and interesting because there are decisions that you need to make in hardware. For example, your hardware cost should not be high. Your decisions should be relatively quick. You need to satisfy the DRAM. Even though DRAM operates slowly compared to the processors, you still need to make decisions very quickly because it's still pretty fast. So how do you make those decisions quickly? By accessing large tables. So there are large tables involved here. How do you minimize the size of the tables, etc.? For example, if your state space granularity is very fine-grained, those tables become huge. For example, number of reads in the transaction queue. They could be up to 128. Do you have one value for every single one of those? That's actually very costly, right? Then you have 128 things that you need to keep track of. And if each constitutes a different state, then that's very expensive, right? How do you index into that table? Because these are multidimensional tables in the end, because you need to index it using all of those state attributes in the end. And we have 8 of those. And if each of them has 128 possible values, that's pretty expensive, right? So what we do is something called generalization, meaning we quantize things such that different levels of the number of reads are actually considered the same state. This is quantization, basically. But this is good for hardware cost, but it's also good for generalization. You don't want to learn separately that a given action is important when you have one read in the transaction queue versus 2 reads versus 3 reads versus 4 reads versus 5 reads versus 6 reads versus 7 reads. Maybe all of them are kind of equal, right? So how do you do the quantization is important, clearly, because maybe equal quantization is not the right thing to do. So there are actually a lot of design choices over here. But quantization is actually good for learning itself, because otherwise you'll have to learn all of those different values in the state space separately. Whereas if you actually quantize, you generalize the state space so that you learn once for that general quantized value. So these are actually fundamental things in learning in general, specifically reinforcement learning, but clearly quantization helps in other learning mechanisms also, as you probably know. Okay. But I think my point here is quantization is not good for hardware cost only, but also learning itself, because it enables generalization. Okay. There are also other things. I should also mention that in all machine learning systems, there is exploration versus exploitation. This is a fundamental thing, meaning you are actually following a policy. Do you actually keep following the policy all the time, or do you actually give room for exploration as well? This means that whenever you actually need to take an action, you always consult the table that tells you this is the action you need to take given the state so that you maximize the reward. That's good. But if you always keep doing that, you may be stuck in some local minima in terms of the policy space. And sometimes you need to explore. Always exploiting may not enable you to learn better. This is also true in human learning, right? If you always exploit your knowledge, how do you learn new things, right? Sometimes you should explore, right? You should actually go and do something completely different, and that puts you in a different space, and you learn something else that enables you to actually do whatever you're doing right now better, right? In research, for example, you read some completely different paper, and that gives you an idea, and that way you can actually do something better, right? Similarly, here we also explore. In this case, exploration is not as wild, potentially, like reading a new research paper that's completely different. But you basically say, okay, my current policy recommends that I should take this action, but I'm going to go against it because with some random probability, I should be exploring so that I can find out hopefully a fundamentally, potentially better policy. So I'm going to take this random action that I choose. That is also legal, of course, among the legal actions that are possible currently in the memory controller. And this is important in learning systems so that you don't get stuck in one policy. And that you need to design the hardware controller to actually do this sort of exploration as well. So you can see the analogy in learning for humans also, right? So don't keep exploiting the same policy over and over. Explore once in a while. I think that's good advice for human learning in general. Okay, so after all of this is done, you can read the paper for more details. Getting the hardware right is not easy also, as you will see. There's a lot of hashing, indexing, et cetera, that you need to do too. But what are the benefits? Basically, we looked at parallel applications, and we looked at essentially the state-of-the-art policy at the time was first ready, first come, first serve, which is the 1.00 point on average. We found out that reinforcement learning buys you about 19%, basically, which is not a bad result, actually, because if you actually get rid of all of the data bus constraints, and they magically are gone, all of the timing constraints except the data bus conflicts, I should say, because data bus conflict is fundamental. You cannot send multiple pieces of data at the same time, otherwise there is no bandwidth constraint, right? And the scheduling is not a problem if you don't have any bandwidth constraint. When we talk about simulation, we'll talk about simulators that used to have such no bandwidth constraints, and as a result, they modeled memory in terrible ways. But essentially, if you have only the data bus constraint, but no other timing constraint, you get about 70% performance benefit. So we're getting 19% of it, which is not bad. And this is a pretty aggressive upper bound, 70%. And I should also say that the numbers may look low because these are applications that we could simulate at the time. Today's applications are much more intensive, and we could have done maybe even more intensive simulations. Okay, basically, we found out that the performance improvements are consistent, and they're also robust over many human design policies. We also looked at policies that use the same information as I mentioned. Okay, any questions? Okay, I'm running much more slowly than I thought, so we'll keep going for a while. Okay, basically, yes. Yeah. You mean the simulation infrastructure? Yes, we built, but this is only simulation. Yes, building hardware for it is very expensive at the time. Yeah. No. You really have a hardware, dedicated hardware that does reinforcement learning in the memory controller. Yeah. Yeah, exactly. There are tables, not terribly large. I think overall 32 kilobytes, but it's really optimized to be built in the memory controller. You can think of this as a hardware accelerator for reinforcement learning built inside the memory controller.
Yeah, and I think they are specialized in the sense that they have an exact number of rows like in the hardware accelerator, right? So it won't be very generalizable, right?
Yeah, it cannot be generally used by any reinforcement learning mechanism, yes. But you cannot build this in CPU because it's too much latency, right, to communicate. In other works that I will maybe later mention, we look at building things in software. So you can actually download those things, but they're not applicable to memory controllers. Okay, so let's talk about advantage and disadvantage of this. Basically, this clearly has performance, etc. advantages because it enables continuous learning in the presence of changing environment and workload. So you're not stuck with a single policy in the end. You have also a reduced designer burden in finding a good scheduling policy. Designer doesn't specify how the memory controller should schedule things, but it only specifies what system variables might be useful in scheduling and what target to optimize, but not how to optimize it. I think this gives a lot of freedom to the underlying scheduler to actually find a good policy. So I think my criticism of existing systems is there is a memory controller on my laptop, which is 5 years old probably right now. It was designed 3 years before my laptop was built. Let's say its age is 8 years, let's say, and it hasn't learned anything. It's doing exactly the same thing all the time. Is that a good design? It's good to think about that, right? It's seen a lot. It's seen lots of workloads, lots of use cases, etc., and it's learned nothing. It's the dumbest thing you could ever find, perhaps, right? Of course, maybe I'm exaggerating, but it doesn't learn anything, right? Okay, so there are, of course, difficulties in this sort of approach. I mean, it was even more difficult like when we were doing this 16, 17 years ago. Basically, how do you specify different objectives? There is work that comes after this, and I think it's important to continue that line of work. Hardware complexity, how do you actually make it lower complexity? Or how do you actually generalize it a little bit so that other things can use it as well, potentially? But I think the hardest parts are really the mindset and flow of the design. Mindset includes like testing, verification, validation. How do you validate or verify these designs is not an easy question, right? Because normally, sometimes when you actually design policies like this, actually not sometimes, usually, when a hardware designer who is a domain expert designs policies like this, they also come up with a set of micro benchmarks. This is a good design paradigm, I would say. You come up with a set of micro benchmarks, and you, based on the policy you designed, you expect some performance or some behavior out of your micro benchmarks that you designed, and you basically do some functional testing based on that behavior. If you don't get the behavior that you expect, either your micro benchmark is wrong or your policy is wrong. Basically, something is wrong. So you figure out what's wrong. But it's relatively easy to figure out what's wrong in that case because you know your micro benchmark, you know your policy exactly. Here, both of those are hard. How do you come up with a micro benchmark? Okay, maybe you came out with a micro benchmark, you have some expectation, but how do you know what to expect, right? Because the policy is changing. Policy has a lot of, let's say, things that you have not controlled. Clearly, you have not designed the policy because it's acting based on its own. It has a mind of its own, literally, in this case. How do you test it? So that testing paradigm is gone, in a sense, right? You could do, of course, lower level testing that doesn't rely on intuition, right? You could, of course, exercise whether the update function is working correctly, whether you're actually doing the right thing, but you cannot really test and verify the policy at a higher insight level. Right? That's the difficulty in design. And this is one of the difficulties of adoption in general. How do I relinquish control of my testing to an agent? Do I trust that agent, etc.? And this is a general issue with machine learning in general, right? In this case, it's about performance, but in many other cases, machine learning is being used for potentially safety critical things. Do I trust that, right? But this trust issue is very fundamental. Even if you do something for like performance like this, there will be people who will not trust what's going on because they don't understand it. So explainability is a big problem in general. Okay, I will not go into this more detail, but this is an area that needs definitely more work. But I think we need more ideas, certainly, and we need to work more on explainability of these issues. But at some level, explainability is also very difficult, right? Because it's very difficult to get complete explainability. You could actually debug. I should also say that debugging is also difficult, right? Because once you start debugging, again, performance debugging, right? We could verify things at a very, very lower level, whether the circuit is working, whether the multiplications are being done correctly, whether the update function is working. But how do you do the performance debugging? If you're not getting the performance that you expect, for example, again, how do you deal with it? What is the policy, right? You could cycle by cycle look at every single value that's in the table that's relevant, but that policy becomes very, very difficult. So we actually really need much better verification and debugging tools to enable machine learning as a fundamental component in hardware design in general. Okay, but that's the paper. And if people are inspired and want to do more work in this area, I think there's a whole lot of potential. And this paper was invited as a retrospective. So if you're interested in our retrospective after 15 years, you can look at it. This was invited last year to ISCA as part of their 25 years of ISCA issue. So there's more work in this area. I'd also recommend people to take a look at this paper, but I believe there needs to be more work in this area. Maybe Rahul knows more work, but is that all? He didn't add it. Like, yeah, I'm going to talk about that, yes, very briefly. So I think this is an example, while we're talking about memory controllers, this is a self-optimizing memory controller, but I think in general, this concept should be applied to more things in architecture. So I'm going to take a critical view of system, especially hardware architecture designed today. It's mostly human-driven. Humans design the policies and they dictate exactly how the hardware should behave, right? As a result, we have many too simple, short-sighted policies all over the system. Memory controller, cache, interconnect, scheduler, whatever you find. Instruction scheduler, all kinds of schedulers everywhere. They're all short-sighted and very simple policies. And there's no automatic data-driven policy learning. This is true for branch predictors also, like prediction mechanisms as well. But people have looked at perceptron predictors, as we have covered in DDCA, for example. But things are getting better, I think. And essentially, there's almost no learning. As I said, all of these hardware components are designed and they see a lot. They have the potential to learn a lot from the data that's flowing through the system, right? But they didn't learn anything over many, many years, right? The question is, can we take a fundamentally different way of take on designing architectures and can we make them better, more intelligent? I don't know what fundamentally intelligent exactly means, but this reinforcement learning agent is more intelligent than FRCFS scheduler, for example, right? So what's an intelligent architecture? It needs to be data-driven. Basically, it needs to learn based on data. Over time, it gets better, hopefully. It learns the best policy, adapts. And hopefully, it has a sophisticated, workload-driven, changing, and far-sighted policies. And we call this automatic data-driven policy learning. And if all controllers are intelligent data-driven agents, maybe you have a much better system. And maybe they need to coordinate with each other also, but that's true even in existing systems, as we have discussed, right? Maybe last level cache policies should coordinate with the memory controller policies, right? Similar to that, I think intelligent controllers should also could be communicating. So I think in the end, we need to rethink the design of all controllers and how we design hardware this way. So this was one of the papers. More recently, Rahul has been leading some work where we applied reinforcement learning principles to prefetching, in particular offset-based prefetching. Rahul can talk more about that. Maybe we'll have some lectures when we talk. Actually, we'll have some lectures on prefetching, so stay tuned. And he's also more recently looked at not necessarily using reinforcement learning, but simpler things like perceptrons to decide or to predict which load request will go off chip. And we've also been looking at using reinforcement learning in stored systems. This is where we have artifacts and software completely, because in stored systems, you need to make a decision on where to place the data in multiple different storage types, for example. And that decision making needs to be intelligent if you want to get better performance, better tail latencies, etc. And this paper looks at that issue. And you can build on it, actually, if you're interested. Okay. So basically, this is the data-driven part of this three things that we have discussed in this course so far. We've clearly discussed data-centric. We're going to discuss more of that. Data-driven is something we have discussed right now. Data-aware is basically how do you actually make the architectures more aware of data. I'm not going to go through this in detail, but you can look at this, and we have papers on this topic. So I mean, we're not saying that we're imitating what's going on over here, but if you actually design architectures that are more intelligent, maybe we're getting closer to what this thing is trying to do, right? I don't think this is using like fixed policies everywhere. It's kind of weird to imagine this is using fixed policies. That goes against the fundamental learning nature of beings, right? Human beings. Okay, so I have a bunch of stuff over here. I wanted to talk about a few things, but if you're interested, I'm going to switch to something, but before that, we'll take a break. But I will mention that we have more material on memory-centric computing. I think next week, Friday, hopefully, we're going to cover more memory-centric computing. But we have an interview on memory-centric computing that was published just today. So if you're interested in a little bit of history of processing in memory and what we think about it, you can take a look at that. The reason I wanted to bring in memory-centric computing is because I'm going to make the memory controller and memory interface a little bit more memory-centric when I talk about this one. But let's take a quick break. Let's be back at 15:21, and I'm going to cover the remaining slides, and then we're going to part today. Does that sound good? All right. Huh? right on time. Okay. So if people want to learn more about reinforcement learning, you can certainly read those papers, especially those hardware-oriented ones. But there's also a nice book by Rich Sutton and Andrew Barto on reinforcement learning. It's all free online. You can find the PDF if you search for Rich Sutton, who's done a lot of work on this topic on reinforcement learning. He has a very nice book on that topic. Maybe we can put it on the website and link it. Rahul can help. Okay. So I want to conclude the memory controller lectures with a work that rethinks the interface a little bit. Not hugely, but I think this is an improvement over the existing interfaces. Essentially, if you look at the interface that I described, memory controller dictates everything, right? A DRAM chip has no freedom. It's not autonomous. It's really basically obeying what the memory controller says. The DRAM chip itself cannot power down anything. The DRAM chip itself cannot refresh anything. It basically obeys what the memory controller does. Maybe internally it does something, like RowHammer protection it can potentially do, but it has to hide it from the memory controller. It cannot make things, make big changes, right? So it has no autonomy in that sense, right? So if you think about it, this goes against all the principles of memory-centric computing that we have discussed earlier. That's why I kind of have these slides over here, right? We've talked about memory-centric computing, but memory is an incapable agent. And that's how we've been treating it for many, many years. So another way of thinking the interface is basically have equal partners, right? Equal partners means they actually can communicate with each other and do a good job in executing a function, right? You basically, the memory controller says, memory, can you do this for me? And the memory says, no, I'm busy right now. I cannot do it, but I'll do it later, right? Something like that. This is more of a equal partner or request-reply type of interface. And memory sometimes can request some things also perhaps from the memory controller, right? God forbid, you cannot ask for that in today's systems, right? Because you'd be violating something really important, which is the processor-centric design paradigm. Processor cannot be asked anything by someone else, right? But processor can ask everything to others, right? If you think about it. So if you think about it, this kind of makes little sense, like the current system design paradigm. And then we ask a lot from memory. We have seen a lot of issues, refresh, RowHammer, latency. We tell the memory manufacturers, it's your problem. Solve RowHammer. Now, does it really make sense to inflict such pressure on memory manufacturers while giving no freedom to memory manufacturers, right? This is a kind of a very bad state of affairs in that sense. Now, I'm no defender of memory manufacturers, as you know, probably. I actually think there are a lot of issues in memory manufacturing, but there's something wrong that's even bigger in the system, which is really how we treat memory and how we interface with memory, right? That's why this work, I think, is important. It took 6 rejections to get this paper accepted to Micro. You'll find it online, but it's going to be presented at Micro by Ataberk. Ataberk, do you want to present it? No. Okay, no? Yeah. Ataberk is going to have much better slides than what I have over here. Oh, okay, yeah. Yeah, now. I asked now, and you gave the right answer, I think. Yeah. Unless you want to present it. Yes. Okay, yeah. You will do a much better job at Micro with much better slides. So basically, that's the idea of this work. I think I've kind of said the idea, right? Memory controller manages everything, including the maintenance operations that someone can rightfully argue that it's the job of DRAM itself, right? What are those maintenance operations? There are at least 3. DRAM refresh, RowHammer protection, memory scrubbing. Memory scrubbing is basically once in a while you go through memory and correct things that may have been corrupted, right? Using ECC, read and write memory locations to basically scrub and make sure that errors are corrected before more errors can accumulate and correctable by error correcting codes, right? That's the idea. These are operations that a CPU chip should really have nothing to do with, in my opinion, right? In a sense, right? But because of the way we divide responsibilities between memory controllers on the CPU chip and memory chips, these operations have to be controlled and dictated by a CPU chip today. So if you want to change these things, it's a painful process. Basically, this requires changes to the memory controller because the memory controller needs to issue new commands to do RowHammer protection, for example, and the DRAM interface so that the memory controller can issue some new commands, right? People have introduced, for example, the refresh management commands, dynamic refresh management commands, etc., to better do RowHammer protection for some definition of better. And more recently, people are introducing this per row activation, which also requires some support from the memory controller. But basically, these require changes to the interface, the memory controller, and the standards, and they take a really long time. Essentially, they become difficult to realize. It requires a new standard or update the standard, and we've already discussed how painful of a process, how political of a process this is, right? You have to go through this committee. There are hundreds of companies that are part of this committee. They don't want to change anything, and any new idea that you want to push through this committee usually gets shot. And as a result, going from DDR4 to DDR5 standard took, I don't know, how many years? 8 years? Maybe longer. Yeah, Ataberk is counting. Like the next standard, who knows how long it'll take, right? Of course, it's not the only, these are not the only changes that go into the standard, but basically change is very slow this way. And the idea in this work is to basically decouple the concerns, right? Have a better interface such that some things can be done internally in the DRAM, especially those things that the DRAM manufacturer can do much better alone themselves. And some other things are done in the memory controller, and they don't necessarily get exposed to memory. And the memory controller doesn't need to tell the memory controller to refresh at this time, right? So this is the idea of self-managing DRAM to enable more autonomous and efficient in DRAM operations. The key idea is very simple, basically. We don't change the interface completely. It's a very simple, small change, which basically prevents the memory controller from accessing a DRAM region that's under maintenance. It could be one or more regions. And the mechanism by which the DRAM chip prevents the memory controller from accessing a region is by rejecting an activation command. If it gets an activate command to a region that it's refreshing, for example, the memory chip says, try again, memory controller. That's it, basically. And you can change the interface such that this delay is predictable or bounded, etc. The paper discusses all of those issues. This way, memory controller doesn't need to tell the memory controller to refresh. Memory controller doesn't need to tell DRAM to refresh. DRAM decides what to refresh, when to refresh, based on the characteristics of the cells, based on whatever it thinks is useful. And hopefully, it keeps the refresh of a particular region that it locks very quick, and the memory controller hopefully doesn't even access that region while the DRAM is refreshing it, right? Otherwise, the memory controller needs to send refresh commands every some number of, I don't know, every periodically, essentially today, right? Okay, so what does this require? This requires a single pin added to the memory controller, or you could abuse the alert pin that we have discussed earlier. I don't like abusing things, meaning abusing something that's designed for some not completely well-specified purpose to use it for some other purpose is probably not that great. Or maybe you redefine the pin such that this pin basically says, I'm going to NAC, meaning I cannot do what you're asking me to do right now. Try again. That's the idea, basically. This way, essentially, any maintenance operation can be implemented completely within a DRAM chip. But this could also enable other opportunities. Perhaps the DRAM chip may be doing computation in a region. It basically says, I'm doing computation in this region. I'm not going to honor your request right now, right? I'm busy with computation. So it could enable other things also, this sort of interface, I think. So in the paper, we talk about how to do DRAM refresh, RowHammer protection, and memory scrubbing. And we also look at refresh as it is done today, fixed rate refresh. We also look at radar-like mechanisms like variable rate refresh that we have discussed multiple times. We look at probabilistic as well as deterministic RowHammer protection. Essentially, if you could do all of these optimized versus non-optimized mechanisms inside the DRAM, almost without changes to the mechanisms that are proposed in the past, except the interface is much more flexible and DRAM can do it internally without the memory controller being in charge. Also memory scrubbing. So the paper has more detail. These are some old results. You should read the current paper. But I think this is essentially one of the major benefits of it. By making the single change to the DRAM interface, hopefully you can enable other changes to be made by the DRAM manufacturers nicely without changing anything else in the interface, without going to the JEDEC standard committee, etc. I like this paragraph from self-managing DRAM. I'm not going to read it, but essentially this gives the DRAM chip a breathing room, right? So that it can autonomously perform maintenance operations. And hopefully future maintenance operations, interface modifications for implementing future maintenance operations become unnecessary in the end. Okay, so if you're interested, this was part of Hassan's thesis, and he has a talk on this topic. And Atabak will soon have a talk on this topic also. That's going to be much nicer than what I just covered. Any questions? Okay, let's see. So in the remaining time, I'll quickly go through memory interference. I will not go through a lot, but this is kind of a foreshadowing of what we will discuss in the lectures next week. Essentially, this is still about memory controllers, but memory interference is a bigger problem. It's not essentially multiple threads interfere with each other when they access memory system. But usually, at least in the past, more and more so, this is becoming recognized, even more recognized problem. But if you design a memory system that doesn't distinguish between different threads requests, you may actually have problems, meaning one thread can deny service to another. So if your memory control algorithms are not aware of different threads requests, for example, different hardware threads requests, they may be unfair to different threads. As a result, aggressive threads can deny service to others, and you may lose system performance also because of this. I'm going to give you one example that we're going to cover in more detail in the next lecture. But we're talking about memory controllers. So we've talked about scheduling policies. Let's take a look at how do you design a scheduling policy for multiple cores. And I'm going to keep this simple. Basically, cores will interfere with each other only in the DRAM memory controller in this case. And we're going to run two applications. Let's say one is a streaming application. The other is a random access application. And this is what we will observe. Random access application gets denied service. And it keeps waiting and waiting and waiting and waiting in the memory controller. And this happens in real systems. Well, it used to happen more in the past. I don't know. I haven't tested the most recent systems yet. But this is because there's unfairness in the memory controller, right? The memory controller is designed for a metric that's not fairness. And this is the stream application that we ran at the time. We're talking about 2006 right now on real systems. Essentially, it has sequential memory access, very high robot-for locality, very memory intensive because we ensure that everything misses in the caches. And this is the control application, which is a random access application, which has exactly the opposite characteristics except for memory intensity. It's similarly memory intensive, but it's random memory access. As a result, it has very low robot-for locality. This is not exactly how you would write the applications because this random function call takes a long time. So if you really want to measure the time of these applications carefully, you should really do some optimizations over here. But you can find that information online in our source code, etc. So what does the memory hog do? So we call this the memory hog program, which basically hogs the memory bandwidth against other applications in general, but also specifically the random access application. If you run these two applications together, assume that they are accessing the same bank. Essentially, streaming application opens the row buffer. It keeps accessing sequential columns in the same row. It essentially accesses row 0. And then a request comes from a random access application. The memory controller deprioritizes that request because it's prioritizing things that hit in the row buffer, right? So a streaming application keeps accessing the same row in the same that is open in the row buffer. So its requests keeps getting prioritized over the random access application that is trying to access different rows in the same bank, but doesn't get its chance because the memory controller is designed to maximize row buffer locality in this particular case, right? And you could keep animating, but it gets boring after some point. Essentially, as you can see, this is a denial of service problem until the streaming application switches to another row or stop accessing this row, or a timeout is enforced, which is not nice in general, timeouts. But it's one way of solving this problem. the streaming application hogs the memory bandwidth in this bank, and random access application doesn't get its request serviced. And you can do the calculations if you want. Essentially, a large number, hundreds of requests of the streaming application may be serviced before a single request of a random access application. We actually did this on real systems at the time we were studying this problem. We ran a streaming application like MATLAB, which does a lot of streaming accesses to matrices, for example. And then we also ran GCC, which is not exactly random access, but there's a lot of random accesses, enough random accesses to see the problem, at least. And these are the slowdowns that we measured. This is on a system that looks basically very similar to what I showed. Caches are not shared, and you have sharing at the memory controller. So you can see that one application slows down a lot more than the other. So it's quite unfair. MATLAB doesn't slow down. This may or may not be a problem, right? Maybe you don't care about fairness. Maybe what you are really trying to prioritize is MATLAB. But if what you really care about is GCC, then you have a problem, right? So basically, this is due to the unfair scheduling policies of the memory controller, the FRF-CFS policy that we've discussed, which is commonly used as a building block of a bigger policy in the memory controller today. It prioritizes row hits first, and then oldest request first. And the scheduling policy, both of these decisions are actually unfair. The policy tries to maximize DRAM throughput, but when multiple threads share the DRAM system, it's unfair. Basically, row hit first unfairly prioritizes threads that keep hitting in the row buffer. Oldest first policy is also unfair because it implicitly prioritizes threads that keep accessing memory a lot, right? Because if a thread floods the memory system with lots of requests to memory, and if another thread has only one request, the thread that floods the memory system is really denying service to the thread that has only one request once in a while, because all of those requests that are flooding the memory system will appear older to the memory controller at some point than a single request from some other thread, right? So both of these policies are actually quite unfair policies. So we've actually run these workloads as stream and random, as you can see, and we see significant slowdown differences. These are the stream and random applications that I showed you earlier. You can think of those as micro benchmarks, but actually these are, again, similar to kernels used in real applications also. So stream slows down little, random slows down a lot. And when you run stream with other applications, you again see similar denial of service behavior. And this becomes a bigger problem with more cores. Essentially, as you add more cores, this slowdown spreads actually increase. So libquantum, for example, is a quantum computing simulator that's very streaming. And it acts like a streaming memory performance hog. So other workloads actually slow down a lot more. This is another benchmark from the spec suite. This is a video encoder, decoder, as you can see. So basically, if you have this sort of unfairness in the memory control, you're vulnerable to denial of service. Someone can actually maliciously write these programs. So whenever you're vulnerable due to unfairness, malice can be at play also, right? Basically, someone can exploit that to actually deny service, starve the others. Just like any resources, even in human systems, right? Humans are terrible at resource sharing in general in the world. So starvation happens in the real world also. And this happens sometimes because of unfairness issues, but sometimes it could be exploited maliciously. And it is exploited maliciously here with the streaming application, right? So basically, it could be denial of service. It could be system level control may be lost because maybe in the system level, I want really this particular video encoding application to get priority, right? But I cannot enforce that because I have no way of communicating to the memory controller saying that you prioritize this thing. And you also get low system performance because your system doesn't progress very well. Meaning this core makes some progress, maybe, but it's very intensive in memory, so it's slow progress. The other cores may not make a lot of progress, right? In fact, if you prioritize some of these less intensive cores, maybe they're going to make much better progress, right? So basically, this is really bad for system performance, overall system performance, or throughput as well. In the end, if you don't control such things, if you design controllers that don't take these into account, you have an uncontrollable, unpredictable system. And this is actually for many applications, and you can see many works on this. We're going to talk more about this in the next lecture, but I'm going to kind of give you an overview of what we're going to talk about. We talked about memory performance attacks. Essentially, we're going to look at mechanisms to control this. How do you solve this problem? Essentially, if you have this uncontrolled behavior, unfairness, starvation, denial of service, in these memory resources, you need to build mechanisms to control it, right? This is not rocket science, this is obvious. It applies to, again, much broader things that are not the subject of this course, but resource sharing is really a big problem. And we basically are going to talk about especially memory controller mechanisms, but we'll talk about briefly mechanisms that are applicable to interconnect and caches. So essentially, we need to design interference-aware, quality-of-service-aware memory system. So we'll talk a lot about quality-of-service-aware memory scheduling. We talked about performance in this earlier, right? But now we're not going to talk about only performance. That's going to be important. How do we schedule requests such that we provide high system performance, high fairness to applications, and also configurability to system software such that the system software can designate which applications get priority, or system software can designate what kind of service level each application should get. Right? This is, I think, a fascinating and important problem. So to be able to do this, your memory controller needs to be aware of threads. Threads meaning hardware execution contexts that are sending requests to the memory controller, right? So we have done a lot of work in this area. I'm not going to cover it because we don't have time. In fact, we have very little time, but these are some of the works that we're going to cover next time. A lot of scheduling, a lot of interesting ideas, a lot of theory behind these scheduling mechanisms as well. And sometimes you get good comments from reviewers also. This is a comment from ISCA 2008 that we got for the PowerBS paper, which ended up being implemented in some SoC memory controllers. Okay, you can read that. Short review, but a positive review. Sometimes it happens. And then there are other papers that we're going to cover. There are a lot of readings that I'm not going to cover right now. But I will end with something that looks like this. Basically, the problem is getting much worse. Essentially, we have all different types of cores, general purpose, and then special purpose. They're all different types. And then massively multi-threaded, etc. And then there's also the I/O access engines, direct memory access, I/O access. They're all sharing the memory controller. Everybody's going through the memory controller basically today. The question is, how do you design the memory controller to provide all of the metrics that are good and also configurability such that the system software can actually configure things? So hopefully I've convinced you that memory controllers are critical to research and there needs to be more done in this area. I believe we need actually more breakthroughs in this area because these will become more important because they're not going to go away. The memory controllers will be there. Increasingly, they will also facilitate computation offloading coming from these different cores. So it'll be another thing, right? On top of memory accesses, you also need to deal with computation offloading that's coming from these cores. So that's why we dedicated one lecture. I thought it would be a shorter lecture, but it ended up being longer, but I think it was important. And next week, we're going to start with quality of service aware system, service quality, but we're not going to forget performance because service quality is easy if you don't care about performance, right? Or you over provision the resources a lot and don't share, right? Then it's very costly. Then you get service quality, but performance is terrible if you think about the resources you're dedicated to it. Performance is always a function of how efficiently you utilize the resources. And we should never forget that. You can get very high performance and high service quality if you don't keep all of your resources busy, but that doesn't mean it's high performance because there are so many resources that are getting wasted. Okay, any burning questions? No? Okay, everybody's ready to go for the weekend. Okay, I'll let you go for the weekend. Have a good weekend. I'll see you all next week.